Thanks everybody for coming. I'm Alkis from Google Research, and this is work that we've done with a bunch of collaborators from Google. So in the interest of time, I'll just start with the summary of the talk, okay? And there are basically 3 points. Machine learning production is hard, and a big part of this hardness, I'll argue, comes from the data side of things. And because of this hardness on data, we need basically to elevate data to first-class assets in our systems, similar to infrastructure and source code. So we need tools to analyze, validate, and track the data that flows in our machine learning pipelines. And we need to take into account the end-to-end story of these pipelines to do this effectively. And last, I'll talk about the tools that we developed at Google for data analysis and validation in the context of the TensorFlow Extended Platform. And I'll also give you a glimpse of the benefits that we're able to reap from having this analysis and validation in place. So first point, doing machine learning in production is hard. And this is something that we've heard repeatedly from different sources. And I'll try to motivate that part, and especially the part that has to do with data, by going over a sample story here, which reflects a lot of the stories that we actually see in production at Google. So the starting point for machine learning is that somebody has data and they have a question that they want to answer using this data, and they think that machine learning is a good way to do it, right? Now this input data, at least in our case, comes from several diverse sources. They can be relational databases, they can be logs, they can be CSV files, what have you, in different formats. But the key point here is that most of the times we're able to assert very few properties over this data because we don't have control over the storage of the data. Another important point here is that we need to draw a distinction between the training and serving side of things. So the training data typically will come in large volumes. The computation that we'll want to do on this data will be batch-based and will be basically focused on high throughput. Correspondingly, there's a serving side of things where the data comes in small quantities. We'll need to do online computation on the data, and there we really care about low latency. And what ends up happening in production is that typically the code paths to access these two sides are different. And this actually turns out to be a big source of problems in machine learning pipelines. And I'll come back to that a bit later. So for the time being, our data scientists will most likely be on the training side of things. And they'll do a bunch of iterations by building a model over the data, looking at the quality of the model, thinking, is this good enough? Do I need to change some of the parameters of the model? Do I need to bring in more data, more features, and so on? This is, the phase where having something like a Jupyter notebook is really useful. And after several experiments, they get to a point where the quality of the model is good enough, and they're thinking, we're ready to launch. But up until this point, our data scientist has dealt with this part of machine learning. Okay, they've built a model. And in order to put this model into production, we argue that they have to deal with a lot more. Okay, and this is where the hardness of running machine learning in production comes from. And in particular, this much more that they have to deal with has a lot of data concerns in it. And again, let me motivate it with a scenario here that is somewhat informed from what we've seen in practice at Google. I'm sure that other organizations have similar examples. But here's an example of a data failure in production. So imagine a system which is already running machine learning in production. It's running smoothly. And at some point, a developer does a refactoring of some backend that generates a feature. Okay? And this refactoring doesn't change the data that is being generated. It doesn't change the model. It doesn't change anything else in the system. Okay? It's supposed to be an innocuous refactoring, a cleanup. And our developer can do their due diligence, so they can run their unit test and integration test and everything, right? And at some point, they go to a production rollout where they have to push the updated version of the binary. But for several reasons, this rollout can fail or can be done partially. And you may end up with a mix of old and new code in production. And this mix of old and new code can introduce some subtle problems. And in this case, these problems led to basically some of these backends failing and returning an error when being called. And then the system taking that error value, which is -1, and interpreting it as a feature value. So right now, we just had a bunch of features just go down to -1 because of that backend failure. And of course, you can imagine that when suddenly you get a feature go to -1 out of nowhere, your machine learning model will not perform really well, right? And the problem here is that these data issues that can happen for many reasons tend to propagate throughout the system, right? So suddenly we had this backend giving us bad feature values. If these bad feature values found their way back to training data, then we start generating models that are based on these bad feature values, and now we have bad models in production. And the more that this propagates throughout the system, the harder it is to recover, right? So it's really important to be able to catch these errors soon instead of catching them late and then try to retrain everything and try to recover. So going back to our sample user, in order to be able to launch their model in production, they have to worry about, can we validate the data that is coming in the system, okay? So what are the properties of the data that significantly affect model performance? Are there dependencies to other infrastructure that we have to worry about and monitor? Another important question is, does the serving data look similar to the training data? Because if it's not, then it means that we're training for the wrong problem. We need to be able to detect when this dissimilarity happens, and there are some interesting questions on how to do this robustly. And every time that we catch a problem, we have basically to raise an alert. We have to notify someone that, hey, your production pipeline is malfunctioning because something is wrong with the data. And we have to formulate these alerts so that they're understandable and actionable because, again, some human will look at them, okay? And we also need to be able to avoid false positives because if we generate too many false positive alerts, this ends up being spam. Our human operators will just switch off data validation because they don't think it's useful anymore. And that's sort of the worst, a very bad scenario. And even when we give them an alert that something is going wrong, we need to make our human users understand how to fix the problem, right? It's one thing to tell them that something is wrong, and but we also need to provide enough context to understand how to fix it. And in our systems, at least, fixing a problem doesn't necessarily mean changing the data in place, okay? The data is stored in some backend system, and usually what needs to happen is that we need to regenerate the data by running some updated code and then backfill our pipeline with a new version of the data. So this in-place update of the data really doesn't exist in the environments that we're dealing with, and this backfilling is actually an expensive process where many things can go wrong. Again, we need to be very careful with. Okay. So after all of these safeguards are put in, then we're ready to launch the model and starts running in production. And several weeks and production fires later, we might have somebody else join the team and basically say, hey, I want to change something here. I want to add a new feature. I want to try a new experiment, so on. And so we need to start this whole cycle all over again. So if we look at the activities or the process that happen here, we sort of identified 3 dimensions that we need to worry about. The first one is what do we do with the data, right? So first of all, we need to understand the input data that we're going to use for machine learning. Understanding the data helps us prepare the data to feed into the model. It also helps us understand what are the important properties of the data in case something fails, and this relates to validation. And also helps us understand how to fix the data if something goes wrong. So all of these activities are sort of overlapping with each other, and we need tooling in each case. The second dimension is that we have different users coming into the pipeline at different points in the pipeline to deal with these problems. So on one hand, we have the machine learning expert who knows a lot about machine learning, and they are the domain expert who will create the models, but they will most likely work together with a software engineer who has more domain knowledge about the particular data set and the particular problem that we're trying to solve with machine learning, and they're the person also doing most of the coding. And then on the far end, we have the site reliability engineer. Okay, this is the person who is keeping the lights on. They're typically responsible for hundreds of machine learning pipelines that are running at any point in production, and they might have to deal with many issues simultaneously. And the reason that we separate out these users is because they need to have different reactions to these problems that will come up in production, and so we need to build tooling to help them with their job. So if something goes wrong the SRE will likely wonder, okay, how do I roll back the pipeline to working state, right? They cannot understand in full detail what the problem is, but they need to react. At the same time, the machine learning expert will look at this and they will need to understand the source of the problem and they will come up with a fix. So maybe we need to change the quantization of a particular feature. And then the software engineer is the person who's responsible to actually implement the fix through this backfilling process that I mentioned, right? So they need to write the code to change the quantization and babysit the backfill and so on. So we need to be aware that these users will be involved with our pipeline and they will need to react differently. And the third dimension is the time in the pipeline's life cycle, right? So these users will be involved at different times as the pipeline is being built and developed, and they will need to do different activities. And also, one thing that is important here is that the same role, say the software engineer, will come into the pipeline at different points in time again and again. So when a new team, when a new member joins a team, for instance, as a software engineer, and they need to change something in the pipeline, they need to be able to ramp up quickly. So they need to be able to look at the pipeline, look at the data, and understand what has been done so far, and get enough context to start being productive. So to recap this part of the talk, I guess what I'm trying to say here is that the data side of the story for machine learning in production is really important. We tend to look at the picture at the very top and sort of focus on the train and serve components and think that these are data flows that we can optimize, and there's a lot of interesting research to do over there. But what I'm arguing is that we should also be looking at the other endpoints, the training and serving data. Because if the data is problematic, it doesn't really matter if we can train or serve fast. We're not going to get good models out of machine learning. And even if the data is not problematic, if we train a model and we want to understand how well it performs or why it doesn't perform well, we need to have a good understanding of the data. So again, it goes back to the data side of things. So to reiterate my previous point, we need to elevate data as first-class citizens on par with infrastructure and source code, and that means that we need to develop a lot of tooling to be able to monitor, analyze, and validate this data. So for the remaining of the talk, I'll tell you how we dealt with some of these problems in TensorFlow Extended. So TensorFlow Extended, or TFX for short, is it's a platform for doing production machine learning that we built at Google. It's currently deployed internally at Google and used by our product teams to iterate, build their models, and deploy them in production. If you're interested in the details, we had a paper recently in KDD discussing the technical parts of the platform. At a very high level, TFX basically instantiates a pipeline of stages, okay? So on the left side of this pipeline, you have your data coming in. On the right side of this pipeline, imagine that you have a model coming out. And every stage of the pipeline performs some different parts within this life cycle or this process of going from data to a model. So for this talk, I'll mostly talk about the head of the pipeline where we do data ingestion, data analysis, and data validation. So for data ingestion, basically we try to help the users easily connect their data to TFX and machine learning. Data analysis helps us users understand the shape of the data, and then data validation is, is there anything wrong in the data? And throughout this, we try to basically provide turnkey functionality so that users don't have to spend a lot of time configuring the system. And we're also trying to codify and enforce best practices for machine learning through this components. So for data ingestion, the problem that we're facing is that we have a set of diverse data sources inside Google, where a bunch of storage systems that teams use to store their data. And all of this somehow has to find its way to the TFX components downstream. So instead of having every team develop their own data connector, we basically define a bunch of standard data connectors where we can also make sure that the data comes in a way that we can control and we can do some additional checks. So we normalize the data to a standard representation so that every downstream component can handle with it. And we also make sure that whenever we do some translation of the data as it's coming in on the training side, we do the equivalent translation on the serving side. And again, this goes back to the end-to-end story that I was mentioning earlier, because we cannot just look at the training side of things. We need to make sure that the serving side of things is also consistent. For data analysis, we're dealing with the problem of gaining some, or helping the user gain some understanding over terabytes of data that themselves can have thousands of features, which is, again, something non-trivial. So to do that, we're basically relying on some scalable algorithms to compute descriptive statistics over the data efficiently, and then visualizing the statistics using the facets tool, which actually has been open sourced, and you can read more about. And the facets tool basically aims to provide a quick overview of the data and, in some sense, prioritize the user's attention to the parts of the data where things might be wrong. Okay, so here, for instance, I don't know if you can see this, but there are some numbers highlighted in red in this screenshot, and this basically is the number or the percentage of the data where this feature takes the value 0. Okay, which in our case might be the default value that we get when something is missing from the data, and this might be a source of concern for the user, right? So we're basically trying to focus their attention to the part of the data where we think that something might be wrong. And of course, facets allows you to look at the data in different, or the data distribution in different plots and forms. Again, to compare data distributions. Actually, this is a case where we're comparing two different versions of the same data across, I think, training and testing. Now, data validation. Here, the problem is that we're, again, we have this huge volume of data, and we need to find if something is wrong with the data. Okay. Now, the problem here is that the formats, the machine learning formats that are common, at least in Google, have limited semantics about what is correct data. Okay. So when we actually get to see the data, we've lost a lot of that information. Not all anomalies will be important at the end, because machine learning, by definition, is robust and can tolerate noise. And again, we need to make sure that whenever we find data errors, we need to make the errors explainable. And to give you an example, if we say that the data distribution changed, this might be a valid error that we caught, but it's not very useful for the human operator who sees the error, right? We'd much rather show an error of the form that the default value for this specific feature has become too frequent. Because again, this provides more context, this is more actionable, the user can go and look at their data and understand what went wrong. If you're interested in more details of why this particular problem is difficult, we have a Sigma tutorial that explains in more detail. So to be able to overcome these problems, we basically took a trick from the database, from database management systems. We started with a very basic notion of a schema for the data. So the schema is our way of codifying what are the expected properties of the data. And if you're wondering why we introduce a schema, recall that we don't actually control the storage of the data. The data is stored elsewhere. We don't know exactly how it's stored. We just have connectors that can take the data from the storage system and import it in some normalized format that is friendly to our machine learning algorithms. Okay. So the schema explains the properties of the data. In this example, I'm basically saying that I'm expecting to see a feature called event, which is required, so it will appear in every example. It takes exactly one value that is of type bytes and has a very specific domain. Okay. Now, this is again a very simple example. Actually, in our schema, we can encode more complicated information, so we can basically say whether a feature appears in training only or the serving side only, whether are there any constraints of the value distribution, and a bunch of other metadata that is useful for machine learning. And in terms of the life cycle of the schema, we infer an initial schema by analyzing the data, and there we apply some heuristics to get a best guess of what are the expected properties of the data. But then the user is responsible for actually curating and maintaining the schema. Okay, so they have to basically vet what we auto-inferred. And as the data evolves, we expect the user to evolve the schema. But at the same time, as the data evolves, we also propose to the user changes to the schema on our side so that we can make this process easier. And one other important feature here is that the schema is designed to be both machine and human readable. So we're trying to make both machines and humans happy and not miserable. So once we have the schema, then doing validation becomes somewhat more tractable. We can basically take the data and compare it against the schema. And here's an example of the schema on the upper side, and a simple example, training example on the bottom side. And whenever we find a deviation between the two, we basically raise an error. Now, the source of the type of error that we raise can be different depending on the disagreement. So, for instance, remember that I don't know if I can show you. Yeah. So remember that the domain of the feature is click on conversion, but in this case, I get a value called impression. Okay. So when we actually do the validation here, we discover this unexpected value, but our heuristics tell us that this is okay. This is not really a data anomaly. This is an evolution of the data, right? It's just that your data now has a new value in its domain, and so we propose to the user when we notify them of this discrepancy, we basically tell them, hey, maybe the right thing to do here is to evolve the schema. Okay, so we're going to basically propose an addition of this value in the expected domain. And we have similar heuristics for other types of features and other types of changes. On the other hand, for the num-impressions feature, we get a float value when we said that it's an int. And our heuristics tell us that this is a much more serious discrepancy. This is a case where something went wrong in the code that generated the data. This is probably a bug that was introduced at some point. So here, we're basically saying, okay, mark the feature as unreliable until you fix it. Okay? And again, this is a change that we proposed in the schema. And now downstream components are aware of this change in the schema, and they can skip the feature if needed. And other engineers on the team can also see that this change happened, and they can avoid using that particular feature. All right, so this is how we capture errors in a single data set. There's an interesting class of errors that happens inside the training logic. So to give you an example, again, remember that num impressions is an int value, and suppose that at some point inside the model, the data scientist decides to take the logarithm of this int value, right? And they're taking the logarithm assuming that the value is always positive because that's what their test data looks like, right? Of course, in production, if something is wrong, if this int value is not positive, then this will throw an exception. It will, depending on the way that exceptions are handled, it can crash the whole model. If this model is running in a multi-tenant system, it can crash the whole server running that model along with other people's, other teams' models. So this is highly undesirable. And notice that there's nothing in the schema that tells us that this should be positive, right? This assumption is sort of hidden in the code. So what we did to discover this class of errors is a kind of testing that combines data and model logic. So basically, we take the schema and we start generating data that conforms to the schema, the constraints of the schema, and we feed the data through the trainer. And at some points, we're trying basically to trigger this kind of data errors. Okay, so this is some form of fuzz testing of the trainer using the properties that we know about the data. And this actually has helped us catch an important class of problems in production. And we can do this before a model gets pushed to production, which is also important. The last thing that I want to mention is that we actually spend a lot of efforts putting in mechanisms that compare the training and the serving side of things. Basically, we're trying to understand whether the serving data is different than the training data. And a big difficulty here is understanding when things become different in a meaningful way. So, for instance, if you're thinking about doing a statistical test like chi-square on the two distributions, that actually doesn't work for us. We have so much data that any difference in the distributions becomes statistically significant and basically results in a false positive. Okay? So we spent a lot of time understanding what would be meaningful difference measures, and how can we get some statistical robustness when we estimate these measures so that we can get good alerts sent to our engineers. And this kind of skew problems actually turn out to be quite common in production because, again, we have typically different code paths dealing with training and serving data. So you might change something in the training code path without doing the corresponding change in the serving path, and that's where this skew arises. And by being able to capture the skew problems, we were able to actually provide a lot of value for our product teams. All right, so to wrap this up, this has been, as I said, deployed inside Google. TFX is used by hundreds of product teams. We're analyzing several petabytes of training and serving data per day. We already have several documented cases where we caught data errors that unblocked our product teams on machine learning. And it's actually interesting that several teams wanted to use TFX just for the data analysis and validation part without even worrying about training and serving. So these were teams that had already their training and serving infrastructure outside of TFX, and TFX was just used for the data validation side. And this is a concrete example where we had one of these documented wins. So Google Play does a lot of personalized recommendations to our users. It's obviously important to get these recommendations right, and the machine learning model is a good way to get these recommendations. And when they started using their machine learning model, they observed that it's performing okay, but not as great as they expected, at least in their offline metrics. And their basic assumption is that what we serve in terms of data is exactly the same or similar data as what we train. And turned out not to be the case. It turned out, again, that we had a discrepancy in the serving and training code paths, which led to fewer features being used, or the wrong kind of the features being used on the serving side. Once we caught that using our machinery and they fixed it, they got a 2% increase in the app install rate, which is pretty significant for this kind of systems. So here are some references if you need to read more details. We'll also have soon on archive the paper on the data analysis and validation techniques that we're using. And again, to wrap this up, production ML is hard. Data is a big part of this hardness, and to deal with it, we basically need to elevate data to first-class citizens. So we need a lot of mechanisms around data analysis and validation. And as it turns out from our experience, there is a very interesting intersection in machine learning and databases with many interesting research problems to solve in order to be able to build these tools. And with that, I can take questions.
Very much, Brian. Does anyone have any questions before I deliver? One question. Drew.
Great talk, thank you. So one quick question about schema validation. So I think your system probably validates schema based on some fixed types and ranges of types and stuff like that. How important is it for you to be able to support user-defined schema validation? For example, say you have a GPS location, so you need to verify that it is a real GPS. Or you have like zip codes or something like that, and you need to verify that it is a real zip code. How important is it for a system to be able to use user-defined schema validation code?
It is important. And basically, we've built some of these custom validations in our schema. So we provide them out of the box for our users. I think what you raise is an important point in the sense that oftentimes the data comes from a source with well-known semantics. And sometimes the semantics get lost as you translate the data through several layers before it reaches machine learning. So the schema is our effort to try to capture some of the semantics at the end of this transformation pipeline. I think one direction that we're considering now is whether we can capture the semantics much earlier, whether we can know much earlier that the data is coming from this store with these properties, and as it's passing through transformations, these properties are not lost. So we have less of a burden on the user to configure this.
Two questions. The first, I think in passing you mentioned that you ingest from different formats and so on. I mean, do you have a magic wand there, or is it like you build adapters like anyone? The second question is, much of what you said, not everything, has a large overlap with many of the data prep software. Like, for example, even Google uses Trifactor, for their data prep or their various data refinement. They're not exactly orthogonal. You may have additional part. Can you be succinct on exactly what the innovation is? I mean, I see many ML related, but they also largely overlap with general data prep, data profiling, like Trifactor and others too. So, comments on that.
So the first question, we don't have a magic wand, but we do provide some declarative methods to go from one data format to another. The difficulty there is that whatever declarative translation we do on the training side has to happen consistently on the serving side. And so you're faced with the differences in the two code paths where we have big volumes and batch processing on one, low volume and low latency processing on the other. We're also constrained in terms of the environment where we need to operate. Basically, we're heavily focused on TensorFlow. So a lot of the infrastructure that we build is specific to that. The second question about innovation. So I think here you're right that there is a lot of overlap. As I said, we took many tricks from the database management book, right? But I think what we do differently is, first of all, we say that errors correspond to software problems. So a lot of the formalisms that we've put in place actually try to capture the cases where these bugs appear in code and get translated to errors in the data. The other thing that we're very concerned about is false positives. We don't want to raise an alert unless we're very certain that this alert is actually a bug in the code that translated to an error in the data. And a characteristic example is that if you go to the data prep or data cleaning literature, you'll see that many times, people use standard notions of statistical deviation when they compare distributions, right? To say that data is different. We tried it, it didn't work for us. We had to be very careful in how we define deviation in statistical distributions and how to measure it statistically and say that we measured a significant deviation in a very specific way that allows us to raise an alert with high confidence.
So are you saying you have found a magic wand to sort of give the right balance between false positive and false negative that's domain independent? Is that the claim?
No, I didn't make that claim. I said that we spent a lot of work. I said that we spent a lot of time and effort for the cases that we worry about to make sure that we don't wake up somebody at night, right, for the wrong reasons.
Let's thank Alkis very much again. So thank you.